Area enclosed by polar curves. Objectives. By the end of this lesson, you should be able to find the area enclosed by polar curves. Alright, let's take a look at this graph right here. So let's assume this wavy function here is a polar curve given by the polar equation r of theta. And let's say I'm interested in finding the area of this sector right here that's enclosed by this polar curve here, r of theta. Now the methods we currently have of finding area between two curves is using with respect to x or respect to y and finding top minus bottom or right minus left, but the equation that we're given is a polar equation, so we could do some converting to get to rectangular coordinates, and then we'd have to break this up because notice the top and bottom function switches here if I'm going to do a top minus bottom situation. But since it's already a polar equation, it lends itself to the polar formula that we're going to take a look at in just a second. But this polar formula is based on the pre-calculus concept of the area of a sector of a circle. So let's just look real quick at a sector of a circle. So something like this would be considered a sector of a circle, just some portion of a circle, and r would be the radius of that circle, so that means I'm assuming this part right here is the center. So r is the radius, and then theta is the angle on the interior of the sector of the circle. So if I were interested in finding the area of this sector, and it could look, right now it looks like a quarter circle, it doesn't have to, so a sector also could look something like this, a little slice of pizza, where here's my radius, and then that's my interior angle theta. To find the area of a sector, the formula is 1/2 the radius squared times theta. But theta has to be in radians. So what we're going to do to find the area of regions such as this, instead of thinking about it as top minus bottom, what I'm going to do instead is think about adding up or slicing this region into a bunch of sectors and adding them up. So one of the sectors, well, I'm going to start with just a few sectors and then see that limiting process to get to an integral. So if I broke it up into these few sectors here, of course they would have to be sectors of a circle. So something like that. That would be my first approximation. Notice I'm missing little portions here and there. So the idea is that if we make the angle smaller and smaller, so this is my theta 1, here's my theta 2, here's my theta 3, my theta 4, my theta 5, etc. So those are all my angles, and then of course the length to get to the polar equation, or that distance, the directed distance, is going to be my r of theta. I can find each of those individual areas of each sector, but if I keep making those thetas smaller and smaller and smaller, so just chopping this region into a bunch of sectors and then adding all those regions together, I can find the exact area of this particular region. So that formula looks like the area equals 1/2 the integral from theta equals alpha to theta equals beta. So in other words, the limits of integration have to be angles in radians. So this first ray here really corresponds to the angle in standard position. So this first ray corresponds to my alpha, and alpha is really this angle right here in standard position. So that's my starting angle, and then it's going to go all the way to the angle beta. So in standard position, that goes from the positive x-axis all the way up here to the second ray. So this is my angle beta. So my integral is going to go from alpha to beta, so the first angle to the second angle, of r of theta squared, where r of theta is my polar equation that was given. So the tricky part here is going to be trying to find these limits of integration, trying to find the angles over which the actual region is enclosed by. Alright, for this first example, we want to find the area enclosed by the graph of r equals 2 plus 2 sine theta. So I've gone ahead and already had this graph sketched out for us. For all the problems we're going to work on today, I'm going to have the graph already here. I really want to focus on the setup. but just so you're aware, for all of these problems, you would be allowed your graphing calculator to graph the polar curve and to evaluate the integral once you set it up. So the focus is going to be the setup here. So here's my curve, 2 plus 2 sine theta, and I want to find the area of the whole thing. Now, when you're graphing your polar curve, the first angle that you substitute in is 0. So the angle 0 corresponds to the positive x-axis here, and when substituting in 0 into this sine function, that makes this right part go away, and we just end up with 2, which we would see when substituting into the calculator as well, that the graph starts right here and heads in this direction. So it's going to start right here on the positive x-axis at 2, which corresponds to an angle of 0 radians, and then it's going to travel in this counterclockwise direction and form this particular polar curve. And then it's going to end right back here at 2, which means it went a full circle, or a measurement of 2 pi. So 0 is where I started, and 2 pi, once I went all the way around, is where I ended. So 0 and 2 pi are actually going to be my limits of integration. Now, we wouldn't normally, draw all of the arcs, but because this is the first, or all of the sectors, but because this is the first problem we're doing, let's really think about what's happening. What's happening is we have a bunch of little sectors occurring. So the first one starting at 0, so the first sector is going to be something like this. So I'm obviously not going to draw them really small because we have to go all the way around. So, this would be the first sector, and then I'm extending out, and so something like this would be the next one. But again, remember, these would all be, infinitely tiny. So, or the angle would, go to 0. We're doing this limiting process to create an integral. But what's really happening is we're creating one little sector and another little sector here, and then another one here and another one here. So we're going in this counterclockwise direction. So I'm just going to sketch out a couple of my different sectors. So again, all of these would have to be actual sectors of a circle, but because they're going to be made extremely, extremely small, they're going to just fit right up perfectly against the actual polar curve. So once I get right here, what's going to happen is I'm going to start creating ones over here until I get back to my last one is going to be down here and get me back to 0, but once I go all the way around, well, now I consider that to be 2 pi. So the formula in general is the area is 1/2 the integral from sum alpha to sum beta of r of theta as a quantity squared d theta. So my alpha and beta are 0 to 2 pi. I want to create sectors starting at an angle of 0, going all the way around, and I want to end up where I started, but I don't want to go from 0 to 0, but in radians, 0 equals 2 pi, so I've gone all the way around the circle, and those are going to be my limits of integration. So from 0 to 2 pi of r of theta, well, this is r of theta. 2 plus 2 sine theta as a quantity squared d theta. So now at this point, I can go in and enter this into my graphing calculator to find the numerical answer. Now when putting this into your graphing calculator, you do want to be exact and put in 2 pi into the upper limit of integration using the pi symbol. But there's no need to be in polar mode or to use theta or any other variable besides x. So we could enter this in on our calculator as 1/2 from 0 to 2 pi of 2 plus 2 sine x squared dx. And that's going to give us the same answer. So it's all about the setup, right? And at this point, theta is now just a variable. So if we switch all the thetas to x's, we'll get the equivalent answer out. So this is the setup for my first polar area. All right, let's move on to the second example. We want to find the area of one petal of r equals 2 sine 3 theta. So this is a rose curve, and it creates what looks like a flower, and this particular flower has 3 petals. And it doesn't matter which petal we try to find the area of because there are symmetry in these rose curves. So I'm going to go ahead and try to find the area of this one petal here that's in quadrant 1. So what I'd be trying to do is I would be finding the area of sectors inside of this first petal. So again, just to start out with, I'm going to try to draw those sectors. or at least the radii of those sectors. So I'm trying to do something like this. I'm trying to start over here and create a bunch of sectors. So that means I'm going to need to find that angle where I need to start at. So the starting angle, try to do it in a different color, is going to be whatever this angle is right here. I'm going to go ahead and call that theta 1. I'm going to be in search of that angle. And I'm trying to find this last angle here. So this angle, we'll call it theta 2. Those are the two angles that we're in search of. So what we have to do to find those angles is figure out where the radius is 0. Because that's where, so it's where my petal started at this initial theta 1 angle. Well, the petal started at a radius of 0. So I need to figure out what angle corresponds to a radius of 0. And then my petal traveled around, and then I need to figure out where the petal, what angle the petal was at when the radius went back to 0. So to trace it out with a different color, what happened was my petal started right here at some particular angle. I'm just going to try to draw an X there. And then it traveled around, and then it ended up back at 0 again. So remember, 0 is called the pole. And the pole is when r equals 0. So I need to figure out the angles that I need to plug in to get out r equals 0. So what that means is we need to find polar zeros. Now on this example, I'm definitely going to take my time to go over this type of problem, but in general this is considered a pre-cal topic. So what we're really doing is we're setting 2 sine 3 theta equal to 0 because I'm taking this r and I'm letting it be 0 to figure out what angles I have to plug in to get this to be a 0. So 2 sine 3 theta has to equal 0. Well, let's divide both sides by 2. If I divide both sides by 2, then I'm setting up a little bit of a nicer equation. When does sine 3 theta equal 0? Alright, so instead of solving this particular problem, instead, let's think about, well, when does just sine of something equal 0? So what angles do I have to plug into the sine function to get out 0 as an answer? So this is like really understanding the unit circle. Sine corresponds to the y values. So what do I have to plug in to get out a 0? What angles correspond to a y value of 0? Happens at a few different places. The first one it occurs at is 0. 0 is one place where if I substitute 0 into sine, I get out 0. And the second place this occurs is at an angle of pi. So when I substitute a 0 in right here, where I put this question mark, sine of 0 equals 0, and sine of pi equals 0. So I'm just going to draw a little unit circle here. So this coordinate point is 1, 0. This coordinate point is negative 1, 0. So these corresponded to angles of 0 and pi. So that's when I have just sine of what equals 0. So what I was really trying to figure out is when does sine 3 theta equal 0. So I just figured out that 3 theta has to equal either 0 or pi for this to happen. For sine 3 theta to equal 0, well, that means whatever was right here had to equal 0 or pi based on our little unit circle understanding. So now, if I want to solve for theta, I need to divide both sides or both answers by 3 because this is like two equations in one. So theta has to equal, well, 0 divided by 3 is 0, and then pi over 3. So in other words, what I just found right here on the graph, it was a little hard to tell, so I drew theta 1 as though it had a non-zero measure, but it turns out that my starting angle is just right here on the positive x-axis. So theta 1 is not actually, wish I could make the eraser a little smaller. I guess that worked out. So theta 1 is actually just a measure of 0. So my first theta 1 is 0. And then it turns out this angle here, theta 2, that we had to find, well, that's pi over 3. And hopefully that should make sense, or it should look accurate to the graph that we have drawn out here. So this is pi, remember, over here. This is pi over 2, which is really a half pi. So it makes sense that this angle in standard position is a third pi, or pi over 3. So if I want to find the area of this one petal, my alpha, or my starting angle in radians, is 0, and my ending angle in radians is pi over 3. So we'll go ahead and write out our area formula. So we're going 1/2 the integral from 0 to pi over 3 of my radius. Well, my radius at any particular point on this petal and on all petals is given by 2 sine 3 theta. Whoops, so we're going to have 2 sine 3 theta quantity squared d theta. Sorry, my writing got a little bit messy. So this is the area formula needed to find one petal of this particular rose curve. Now, just to kind of talk about, well, what if we were asked to find the area of all 3 petals? It wouldn't be necessary to go ahead and find all of these angles here, so the angle here and here, so this major angle and this other angle in standard position. It wouldn't be necessary to do that because of the symmetry. So once we found the area of this one petal, if there was an extension question of find the area of all the petals, the entire curve, I would just need to multiply this setup by 3, given that this particular rose curve has 3 petals. Alright, next example, find the area of one petal of r equals 4 cosine 2 theta. So another similar type of problem, we're going to have a rose curve. We only want to find the area of one petal. This one's just going to be slightly different. So my initial starting value, when I substitute in 0 into this particular curve, my starting value is going to be right here at 4. So when I think about breaking this up into sectors, my first sector moving counterclockwise is going to look something like this. So they're going to start extending out like this. So what I can do to find the area of one petal, well, if I think about what I just drew right now, if I find the area right here of this particular portion of the petal, half a petal, then I could just multiply that number by 2. So now ideally what I need to find is this ending angle. So my starting angle is 0 for sure. That's where I know this particular rose curve started when I initially graph this thing out. So theta equals 0 is my starting angle, and now I need to find this theta 2, this second angle where the curve gets back to my polar 0, to my pole. So I need to set this function 4 cosine 2 theta equal to 0. So 4 cosine 2 theta equals 0, so I could figure out my polar 0. Divide both sides by 4, it's like saying, well, when does cosine 2 theta equal 0? So when does cosine equal 0? So not cosine 2 theta, again. So we're mentally just thinking about when does cosine theta equal 0? Well, that happens at angles of pi over 2, 3 pi over 2, and then we can keep going with coterminal angles. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. But I'm going to stop for now at just these 2 angles. So these 2 angles, I'm going to put it in parentheses to remind ourselves that these 2 angles are really solving when does cosine theta, whoops, I don't want to write theta 1. When does cosine theta equal 0? That's where these 2 solutions are coming from. But again, what was I really interested in? When does cosine 2 theta equal 0? So I need to let 2 theta equal these answers to when cosine theta equals 0. So I'm just going to divide both sides by 2 to find the actual thetas that go here that I'm looking for. So theta equals pi over 4 is one of the options if I divide by 2, and then 3 pi over 4 is another option. So let's take a look back at our polar curve. That would mean that this angle here, pi over 4, is our upper limit of integration, and hopefully it does make sense to you. It looks like it's chopping this first quadrant right in half, so remember that this is pi over 2, and it looks like this angle right here is half of that, so pi over 4. And then what did we find in the second answer? Well, we found this other polar 0. So 3 pi over 4, which is the angle that goes all the way over here, that's my other angle. So what I can do to find the area of one petal, at this point, because I found these 2 answers, I have a couple different ways of setting this up. So let's go with what we initially said. So let's find the area of this little green outlined part. If I extend, so we have 1/2 the integral from 0 to pi over 4 of my radius, so there's my polar equation, 4 cosine 2 theta quantity squared d theta. So what this finds is this green area. I want an entire petal, so I would need to double it. So I would need to multiply this by 2. So that finds the area of one petal. But because when we found our polar zeros, we actually happen to find this other angle right here, if I extend from pi over 4 to 3 pi over 4, then I'm finding all of these sectors in another petal, which is, because of symmetry, equivalent. So another way I could set up the area formula is 1/2 the integral from pi over 4 to 3 pi over 4 of 4 cosine 2 theta squared d theta. Now, I don't want to multiply this by 2 because in going from pi over 4 all the way to 3 pi over 4, I'm finding the entire petal. So all of these sectors across the entire thing using an integral, I don't need to multiply by 2. It's the entire region itself. So these two will give me the exact same answer if I were to substitute them into my calculator. So there's often going to be more than one way that we can set up these integrals when they have to do with rose curves, because there are multiple petals. In this next example, we want to find the area of one loop of r squared equals 4 cosine 2 theta. So because we have an r squared here, when we enter this into our calculator, we're going to have to solve for just r, which means we're going to have plus or minus the square root of 4 cosine 2 theta. So you're going to enter this in as an r1 and an r2, but what you're going to find, if you were to just graph the positive version, so let's say you enter r1 equals radical 4 cosine 2 theta, and then r2 as negative radical 4 cosine 2 theta, here's what you would find. If you just entered r1 in first and you didn't allow the second one to graph, you'd actually see a function that is sort of cut off in the middle here, and that's because of something called your theta step size. And what you're going to have to do is make that theta step smaller to see the complete graph, which looks like this sideways 8. So you're going to have to change your theta step to something pretty small, like 0.01, but it will take a bit longer to graph when you make your step size smaller. So don't go crazy and put 1,000th or 1,000,000th. It's going to take forever and make your calculator freeze up. So if you were to graph R1, just R1, and change your theta step, you would see this complete figure 8 here. So what does this second equation then do? These are actually going to graph the exact same polar curve. So this sideways figure 8 is graphed by both of these functions, and the only difference is how they're graphed. So this one here, R1, I'm going to go ahead and put a little purple asterisk right there next to it. R1 starts right here at 0. So when I substitute in 0 here, cosine of 0 is 1, and 4 times 1 is 1, and the square root of 4 is 2. So at an angle of 0, my starting point is right here at positive 2. And then it's actually going to travel this way. So it's going to head in this counterclockwise direction. And then it's going to keep going over here. And that's the route that it's going to take if you consider the positive version. If you consider the negative version, what's going to happen is I'm going to have an initial directed distance that is negative. So my starting location is going to be over here instead. And the path of which this particular loop takes is going to be a different path, but it's going to end up with the same exact curve. So that's the only difference here. I'm going to choose to only deal with the positive version, and then when we set up the final equation, we'll see why it didn't really matter in the first place, or it doesn't really matter ultimately anyway. So we're going to stick with just analyzing this first equation. So we know the first equation travels in this counterclockwise direction and starts at 0, and we like when things start at 0. I want to find the area of one loop, so let's focus on this right loop. if I thought about drawing my sectors are going to start looking like this. So we're going to use that same strategy that we did in the last one. Let's just find the area of half this loop and then multiply it by 2. So we're going to need this polar 0 here. So I'm going to need to set the square root of 4 cosine 2 theta equal to 0. Well, in order for this left side to be 0, I need what's under the radical to be 0, or I could think about squaring both sides. So ultimately, I just need 1 does 4 cosine 2 theta equals 0. Divide both sides by 4, and this should look familiar. To the last problem, we have 1 does cosine 2 theta equals 0. And we actually found answers to this in the last problem. We had to set 2 theta equal to pi over 2 and 3 pi over 2. So dividing both sides by 2, we got answers of pi over 4 and 3 pi over 4. So pi over 4 corresponds to this one here. So this angle here, this ending angle, is pi over 4. And then 3 pi over 4 is this other polar 0 over here, which we're not going to need because we're only thinking about this little region here. So we're going to set up our integral from 0 to pi over 4. And we're going to have that 1/2 in front for now, so we don't forget it in general. And then we're going to have our function squared, our r squared. Well, our function is the square root of 4 cosine 2 theta as a quantity squared d theta. And that only finds me half of the loop, so I'm going to need to multiply this by 2. But notice what's going to happen. I have the square root squared, so I'm just going to end up with 4 cosine 2 theta, and the 2 and the 1/2 will cancel. So we just have 0 to pi over 4 of 4 cosine 2 theta d theta as the integral that finds the area of just one loop. And now let's think about, well, what about that negative that came up? Well, since I'm going to take the radius, no matter what it is, and square it, the negative would square away anyways. So that's sort of why it didn't matter that I ignored the other portion. It graphed the exact same curve, so just handling or dealing with the positive part made my life a little bit easier and still allowed me to find the area inside of one loop. Alright, now we move on to some different types of examples. So we're going to first try to find the area of the inner loop of r equals 1 plus 2 cosine theta. So here's this graph of 1 plus 2 cosine theta. And the first thing we're going to try to do is find the area of just this little inner loop. And then we want to find the area enclosed minus the inner loop. So we want to find all of this area here and then subtract this little inside loop part. So both of these problems are dealing with this same equation, this same graph. So to find the area of the inner loop, well, let's think about what happens when we start plugging in different angles. When I plug in 0, and if you were to graph this on your calculator, you would know that this graph starts at a directed distance of 3. So at the angle 0, my starting location is right here. So if I were to start creating sectors to find areas starting at 0 and then moving counterclockwise, the first sector I'm going to create is going to look something like this. And then as I continue to move along, I'm going to have all of this area that's accumulating in these sectors until I get to the pole. So I'm going to need to find those polar zeros again, because I don't want all of this area out here, at least not yet for this first part, for the area of the inner loop. I want to start adding up these inside sectors to this inside loop. So I'm going to need to find the first time. So remember, I'm traveling counterclockwise here. I want to find the first time I get to my polar 0, and then I'm going to travel around this loop, and I want to find the next time I get to this polar 0, and those two polar zeros are going to be my limits of integration. So I'm going to need to set this function 1 plus 2 cosine theta equal to 0 to solve. So I'm going to subtract the 1 and divide by 2. So I'm really trying to figure out, when does cosine theta equal negative 1/2? So again, this goes back to a pre-cal problem. What angles do I plug in to cosine to get out negative 1/2? Well, cosine is negative only in quadrants 2 and 3. So the two angles that I need to plug in are going to have reference angles of pi over 3. So we're looking at 2 pi over 3 and 4 pi over 3. So graphically, 2 pi over 3 is over here in quadrant 2, and then 4 pi over 3 is over here in quadrant 3. So those are the rays that really we're talking about, these angles in standard position here. So they correspond to where I go back and hit my polar zero. So these are going to be my limits of integration for the first part. Let's go ahead and call that part A. So for part A, my area formula is going to be 1/2 the integral from 2 pi over 3 to 4 pi over 3, and then my radius function, or my radius equation, my polar equation squared. So 1 plus 2 cosine theta squared d theta. So this tells me the area of this inner loop here. And now in part B, I want to find the area enclosed, so all of the area here minus the inner loop that we found in part A. So the integral in part A is going to be part of our setup right now. It's going to be the part that I subtract. So remember, when we first started, we said, well, if I were to start adding up sectors starting at 0, those would be right here, these green ones. So notice, if I add up all these green sectors, I'm now adding up, and doing so, the area of the inner loop, and that's the part that I'm going to subtract out that we found in part A. So to find the area of the green sectors here, I'm going to go from 0 all the way to 2 pi over 3, because remember, at 2 pi over 3, that's where I hit a polar 0. So I travel left, and I went all the way to 2 pi over 3. At 2 pi over 3, that's when I started adding up the red sectors, all the way until I got to 4 pi over 3. And at 4 pi over 3 all the way until 2 pi, that's going again to those outer sectors. So once I go past 4 pi over 3, now I'm starting to go to this outside part. So to find all of the area of the green sectors here, I'm going to go ahead and set up my integral. So I'm going to have 1/2 the integral from 0 to 2 pi over 3. And then my radius is 1 plus 2 cosine theta squared d theta. So notice all I've done here is find just this top half. But all of this includes this inner loop. So I'm going to go ahead and multiply this integral that I currently have set up by 2, because now that's the entire shape. And then I'm going to need to subtract the red integral. So I'm just going to go ahead and subtract. I'm going to have to do it below because I'm out of space. 1/2 the integral from 2 pi over 3 to 4 pi over 3, 1 plus 2 cosine theta squared d theta. So this entire integral, or these two integrals subtracted, is going to give me the area of, let me attempt a third color. So excluding this part, but all of this part out here. So this got really messy, but all of this part out here is what B solves for. So first it was just the inner loop, which required me to find the polar zeros, and then I could take that answer and carry it to the upper limit of integration for the second integral, and there was no need to really write the area of the whole thing as two separate ones. I could just find half of it and multiply it by 2. So on these problems, we're going to want to try to use symmetry as often as we can to end up having smaller setups. Alright, so now we're going to look at this set of problems here. So I'm going to find the common interior of r equals 3 sine theta and r equals 2 sine theta. So now I have this set of polar equations. And first I want to find the common interior. So it's like, imagine if this is a Venn diagram. So I'm trying to figure out the area of the region of intersection. What do they have in common? And then I want to find the area inside of one of the graphs, one of the polar equations, but outside the other polar equation. So first let's label these, and again, I've been giving you the graph, so you would graph these on your graphing calculator. This one here is 3 sine theta. So I'm going to write close to that 3 sine theta. And this blue graph here is 2 minus 2 sine theta. And the first one we're going to solve is find the common interior. So that is this region here. That's what I'm looking for. And what I'm going to need to do is figure out these points of intersection, or really the angles where they intersect. So I'm interested in the angles where these two graphs intersect. So what is this theta? So I'm going to set these two functions equal to each other. 3 sine theta is going to have to equal 2 minus sine theta. And then we're solving for theta. So I'm going to go ahead and add the sine theta to the other side. So I'm going to show all my work here. 3 sine theta plus sine theta equals 2. And now 3 sine theta plus, this is like 1 sine theta, is, whoops, I don't know how it turned into cosine, is 4 sine theta, and that has to equal 2. So now sine theta has to equal 2 divided by 4 if I move the 4 to the other side. So 2 divided by 4 is 1/2. So when does sine theta equal 1/2? So this only happens in quadrants 1 and 2, and the reference angle is pi over 6. So theta equals pi over 6 and 5 pi over 6 are those two angles. So this angle here is pi over 6, and this one over here is 5 pi over 6. Alright, so the idea here is that what we're going to do is we're going to first add up the sectors, and this is going to be a very small region, the sectors that go from 0, so 0 radians, up to pi over 6 radians on this reddish graph first. So in other words, I'm adding up, I'm going to try to draw as many as I can because it's a small sector, I'm adding up all of the little sectors from 0 to pi over 6 on this graph of 3 sine theta. But then the function switches off. Then I need to start looking at what happens between pi over 6 and this 90-degree angle up here, which means it's pi over 2 on the blue function. So for part A, so let's label these parts again. Here will be part A and here will be part B. For part A, I'm going to need 1/2 the integral from 0 to pi over 6 of this reddish function. So that one was 3 sine theta. So 3 sine theta quantity squared d theta. And then I need to add to it, let's go ahead and change color. So now I'm thinking about adding up all of these sectors starting at pi over 6 going all the way to pi over 2. So why am I going to stop at pi over 2? Because of symmetry. So if I really wanted to, I could say from pi over 6 to 5 pi over 6 of the blue graph, and then go and say 5 pi over 6 all the way to pi of the red graph again. But because I know there's this symmetry that's happening here, what I'm ultimately going to do is multiply this whole setup by 2. So I'm going to go from pi over 6 on this next integral, so 1/2 the integral from pi over 6 to pi over 2 of now this blue function. So the blue function was 2 minus 2. Oh, I copied down the function wrong the first time. Not 2 minus 2 sine theta, 2 minus sine theta. Sorry about that. Alright, 2 minus, whoops, sine theta. But we use the correct function up here and we set them equal to each other. I just copied it down wrong here. So 2 minus sine theta as a quantity squared d theta. Sorry about that. So these two integrals find only half the area, so I need to multiply this whole thing by 2. Or really, that's like multiplying each one by 2. I'm doubling the red part and I'm doubling the purple part. So it's like if I multiply this by 2 and this by 2, it's like getting rid of the 1/2 altogether. So imagine I'm just ignoring the 1/2. So I'm just adding the two integrals, 0 to pi over 6 of 3 sine theta quantity squared, and then pi over 6 to pi over 2 of 2 minus sine theta quantity squared. So this is the setup for part A. So now let's take a look at part B. Alright, I cleared some space off up here. Let's try to work on part B. Find the area inside r equals 3 sine theta. So I want to be inside this red circle here, but outside r equals 2 minus sine theta. So I want to be outside of the blue graph, but yet still inside the red one. So the region that I'm now trying to find is this one here. Alright, so finding the area completely inside the red graph is going from 0 to 2 pi. So I'm starting at an angle of 0. I start right here, and then I travel counterclockwise. And if I complete the entire circle, I end up back at 0 again, or 2 pi. So finding the area interior to 3 sine theta can be found by setting up 1/2 the integral from 0 to 2 pi of 3 sine theta quantity squared d theta. And then what I need to do is subtract this portion here, which happens to be the answer in part A. So I want to get rid of this portion here that I over accounted for when I found the area interior to this entire circle. So when finding the area interior to the entire circle, I was adding up all of these sectors. So then now I need to go back and subtract that region. So what I'm really doing is subtracting this integral setup from A. So it's this integral minus the integral from 0 to pi over 6 of 3 sine theta quantity squared d theta. And here I just need to be careful about how I set this up. So it's minus this entire quantity. So I'm going to keep a big set of brackets around the next part, and then add plus pi over 6 to pi over 2 of 2 minus sine theta quantity squared d theta. So it's the whole circle minus the common interior that we found in part A, and I wanted to make sure and subtract that entire part. So I needed to keep this subtraction outside the big bracket so that I know it would distribute. And just so you know, I'm sorry, I'm sick and I was trying to hide it, but I think it's coming out a lot in my voice right now. Alright, next problem. Find the area of common interior of 3 cosine theta and 1 plus cosine theta. So we want to find what they have in common. So the region that I'm trying to find here is this one right here. So in other words, I'm going to need to find these points of intersection again in order to break this up. So I'm going to need to try to do it over here this time. 3 cosine theta equal to 1 plus cosine theta. So I'm going to go ahead and subtract the cosine theta this time. So if I subtract 1 cosine theta from 3 cosine theta, I'm going to have 2 cosine theta equals 1, or cosine theta equals 1/2 if I divide by 2. So cosine theta equals 1/2 at pi over 3 and at 5 pi over 3. So in other words, right here, this one is 5, oops, not 5 pi, this one's pi over 3. Sorry about that. It's a weird pi. And then this other one's in quadrant 4, and this one is 5 pi over 3. So these are the two, I shouldn't say points of intersection because it's really the angle at which these two graphs intersect. And I'm going to need that point, or that value, this angle, because the first sectors that I'm going to add up are going to be on the blue graph. So we didn't label them. The blue graph is 1 plus cosine theta, and the red graph is 3 cosine theta. So right here, this is where 1 plus cosine theta begins. This is a starting location. So if I think about adding up all of these different sectors, I'm going to go from 0 all the way to pi over 3. And that's going to give me the first portion of the region that I'm trying to find. And then I'm going to have to go from pi over 3 all the way to pi over 2, which is going to give me the remaining portion of the half that I'm going to find, and then ultimately just multiply by 2. So my area setup, I'll change back to black to indicate I'm doing this first portion first. So I'm going to have 1/2 the integral from an angle of 0 to pi over 3 of the blue function 1 plus cosine theta quantity squared d theta, plus 1/2 the integral from pi over 3 to pi over 2 this time. So we're working on this interior portion, which corresponds to the red graph. The red graph was 3 cosine theta, quantity squared d theta, and that only found the top common interior portion. So I need to multiply this whole thing by 2, or each of these by 2, which is really just like getting rid of the 1/2. So the 2 times the 1/2 would make that a 1. So adding these two integrals together, we'll find this area of common interior. And finally, we're going to work on an AP-like question. So a polar curve is defined by the equation r equals theta plus sine 2 theta for angles theta between 0 and pi. So I want you to take careful note of that for these graphs so far, we've been graphing them on 0 to 2 pi, but this one's specifically telling you to look at it from 0 to pi only. In part A, we want to find the area bounded by the curve and the x-axis. So here's the curve. This is the polar equation r graphed out, and I had to go into my calculator and limit it to only go from 0 to pi, because by default it's going to travel along the whole unit circle 0 to 2 pi. So this is my starting location right here at this angle of 0, and it travels all the way around to an angle of pi. So I want to find the area bound by the curve. So in other words, my sectors are going to start out like this, and they're going to continue all the way until I get to pi. Whoops, apparently they got a little crooked. So the integral that I'm setting up for part A is actually not too bad. So it's going to be 1/2 the integral from 0 to pi of the polar equation, theta plus sine 2 theta, quantity squared d theta. And of course you would actually solve for this, plug it into your calculator to find a numerical answer, but we're going to focus on, again, the setup. So now for part B. Find the angle theta that corresponds to the point on the curve where x equals -2. So we have to remember that these polar curves, even though the points on them are polar coordinates, we're still on an xy plane. As you can see, here's a little x, here's a little y. And this -2 corresponds to a particular point on the polar curve, and points on the polar curve correspond to a particular angle. And that's what this question is asking me to find. What is the angle that corresponds to the point on the curve when the x value is -2? So how are we going to find this angle is the question. So for part B, we need to somehow relate x equals -2 and this polar equation that we have. So let's just write the polar equation. R equals theta plus sine 2 theta. Now, we don't want to get rid of the theta because theta is what we're trying to find. So we can't plug -2 into r because it's an x value. So we have to use the relationship that we know that involves polar and rectangular coordinates, specifically x and r. So what we know is that x equals r cosine theta. So if I want to replace r with something to do with x's, I'm going to divide this by cosine. So x over cosine theta equals r. So I'm going to go ahead and replace r with x over cosine theta. And that equals theta plus sine 2 theta. Well, now x is -2, so -2. Now I'm going to move the cosine theta to the other side, so I'm going to multiply it. So -2 has to equal cosine theta times the quantity theta plus sine 2 theta. So when does this happen? Well, we can think about this as two separate functions, and we can graph -2, that's a horizontal line, as y1, and we could graph this as y2, but just replace the thetas with x's. So we're going to go back to rectangular coordinates here. So this is like y2 of x and y1 of x. So we're going to get a polar mode, and we're just going to go back to function mode, as in rectangular functions, and we're going to graph these two and set them equal to each other. Alright, so I've already entered both functions into my graphing calculator, -2 and then cosine x. Make sure you use parentheses here, x plus sine 2x, and then I'm going to go ahead and hit graph. And I'm looking for a positive angle, so I am going to look at this right-hand side, and there's 2 points of intersection. We're going to go ahead and take a look at the first point, or find the first point. So second calc, 5 for intersect. So I'm going to go ahead and move along my curve towards that first point of intersection, that first positive one. Enter, enter, enter. And we have 2.786. So at theta equals 2.786, and I didn't mention it, but you do need to be in radian mode. So 2.786 is the angle. Now, it is in radians, so we're not going to put a degree symbol in here. And we chose the first point of intersection because the other one actually doesn't lie within this quadrant, because this curve r of theta, we only looked at it between 0 and pi, but it actually continues down, does something like this. So there's going to be another place where the curve has an x value of -2, so we want the first place that happens, which is why we chose the first point of intersection, 2.786. Okay, finally, let's answer part C and D. I needed to make some space, so remember, this is my function r of theta. For part C, for angles between pi over 3 and 2 pi over 3, dr d theta is negative. What does this say about the graph on this interval? So they're asking us to make sense of this derivative, dr d theta. So between pi over 3 and 2 pi over 3, let's sort of sketch that out. So pi over 3 is maybe about right here, and then 2 pi over 3 is maybe about right here. So let's say this is pi over 3, this is 2 pi over 3, and this is just for us to help us try to understand what might be happening. We're told dr d theta is negative. So this is a derivative, this is a rate of change. So what it's saying is that the rate of change of r, so let's think about what the variable r represents. R is the radius, or the directed distance from the pole, from the polar origin. So r is the directed distance from the origin, so this is the rate of change of r, the directed distance from the origin, with respect to the angle theta. So as I move along from pi over 3 to 2 pi over 3, dr d theta, the rate of change, is negative. So what that means about r is that r is decreasing. So remember, if the derivative of something is negative, the original something is decreasing. Well, that something is r, is the directed distance, is the radius. So if dr d theta is negative, r is decreasing. But we don't just want to put that. We want to explain what this says about the graph on this interval. So what that means is that the actual graph, the curve, is getting closer to the pole. So the distance from the polar origin is shrinking. So I'm moving towards the pole. That's what's happening on the graph. So for part C, we want to say something like, if dr d theta is negative, then r is decreasing. So the graph is moving toward the pole. Or we can say something like, the distance from the curve to the pole is shrinking. So ultimately that's what's happening. And if we just look at different points on the graph, so looking at this point at pi over 3, look at this distance here, and as I move to 2 pi over 3, now this distance is getting shorter every time. So we don't just want to say dr d theta is less than 0, so r is decreasing. What does that mean about the graph? It means the graph's getting closer to the pole. So that's the answer to part C. That's a conceptual understanding type of problem, but it's something that we've seen way back since chapter 4, but now we're just applying it to different variables. So r, we have to remember, is the radius, of course, so r is given by this function at any angle, but r in terms of polar coordinates is the directed distance from the origin, that radius. And then finally, part D. At what angle in the interval from 0 to pi over 2 this time, so changing up that end angle again, is the curve farthest away from the origin? Justify your answer. So I'm looking for the angle where the curve, where the r value, the curve is r, where the curve r is furthest away from the origin. So in other words, I'm trying to maximize R. When is R the absolute furthest possible point away from the origin, the pole? So it looks like it probably happens somewhere about here. So I'm going to need to justify that though. I'm trying to find a maximum, technically an absolute maximum, on a closed interval. To find an absolute maximum on a closed interval, I'm going to need to find critical points. So ultimately, I'm going to need to test R of 0, what happens at R of pi over 2, and then R of any critical points. So critical points is where the derivative is equal to 0. So R prime of theta is what I'm going to need to find and set equal to 0. So R prime of theta is 1 plus 2 cosine 2 theta. So I'm finding the derivative of this function R here, but I'm taking the derivative with respect to theta. So I don't need to do that whole process for finding dy dx. That's not what I'm trying to find. I'm trying to find R prime of theta. The variable is theta, so there's no need to do any other type of differentiation. So 1 plus 2 cosine theta is the derivative. I want to know when that equals 0. So let's subtract the 1 and divide by 2. So we're setting cosine 2 theta equal to negative 1/2, which means 2 theta is going to have to equal whenever cosine is negative 1/2. So cosine's negative 1/2 at 2 pi over 3 and at 4 pi over 3. So dividing by 2, when theta is 2 pi over 6 and 4 pi over 6. Well, this reduces to pi over 3 and 2 pi over 3. So these are the same as pi over 3 and 2 pi over 3. Sorry, running out of space here. Well, pi over 3 is the only one I care about because that's the only one between 0 and pi over 2. So we already said, or we labeled it for ourselves, that this was about pi over 3 right here. So pi over 3 is my critical value that's in my interval that I need to test in R. So R of 0, well, if I substitute 0 into this function, and we can do this on our calculator, we would get out 0. That one's pretty easy because 0 plus sine of 0 is 0. R of pi over 2 is actually going to get us pi over 2, which is in decimal form 1.571. And if I substitute in pi over 3 up here, I'm going to get 1.913. So I have to find each of those values exactly so that I could figure out which one's the biggest, because then R is the furthest away from the origin. So that happens right here. So the answer, though, is the angle. So at what angle does this happen? At pi over 3. So pi over 3, so theta equals pi over 3 is my answer. And the justification isn't showing this work. So there's no need to summarize your results. Justify just means show all of the work. So we would need to find this test or this critical point and then test it in the R function, including the endpoints as my justification.